All right, welcome everyone. Great to see a full house. It is my great pleasure to introduce Jeff Dean, who is Google's chief scientist. He joined Google in 1999, where he's been building and co-designing, co-implementing the pillars of Google's distributed technology with systems like MapReduce, Bigtable, Spanner, and TensorFlow, more recently Pathways. In 2011, he co-founded the Google Brain team, and since then his focus and research has been on systems and applications for AI, and today he's going to tell us about important trends in AI. And I should also mention he's won many awards. He's the recipient of the ACM Prize for Computing, the IEEE von Neumann Medal, the Mark Weiser Award, and he's an ACM Fellow, amongst many others. So we are very, very excited to have you here, in case you can't tell by the turnout, and very much looking forward to your talk. So a warm welcome to Jeff Dean.
Thank you. Thank you so much for the delightful introduction. I'm really excited to be here, and I'm going to talk to you today about important trends in AI. How do we get to where we are with the current state of what models can do? What can we do now that sort of the field has advanced to the current level, and how can we shape what we want AI to do in the future? And this is joint work with many, many people at Google and elsewhere, so it's not all my work. Many of it is collaborative work. Some of it is not necessarily my work, but I think it's an important set of work to sort of discuss. Okay, so some observations, most of which are probably reasonably obvious to you. So I think most importantly, machine learning has really changed our expectations of what we think of computers as being able to do. If you think back 10 years ago, computers could barely see with the sort of rudimentary computer vision performance. Speech recognition worked, but not super well. Language understanding in terms of language models was kind of somewhat limited in terms of its capabilities. But what we've seen over the last 12, 13, 14 years is that increasing scale of both the compute used to train the models, the data, and the model size, increasing those things generally delivers better results. There's almost a truism to that in many ways, where we've seen this over and over and over the last 15 years, that bigger model, more data gives you better performance in problems we actually really do care about in terms of capabilities of computers. And algorithmic and model architecture improvements have also been really important in this. So it's not just a throw more hardware at the problem kind of thing. Algorithmic and model architecture improvements have actually been even more significant than just the hardware improvements we've seen in the last decade. And finally, as a sort of result of all of this, the kind of computations we want to run on computing hardware are really changing, and how we think about building the computer hardware to run kind of the applications of today and tomorrow is really shifting from traditional CPU-based computation. Okay, so first, I'm going to go through a section that is a whirlwind, one slide per advance. Oh, I should relaunch Chrome within 2 days. Hang on, I agree I should probably relaunch Chrome, but let's try to not do it right now. So a whirlwind of 1 or 2 slides per particular technique that has been really influential in getting modern models to how they came to be. And let's just launch right into that. And it's going to be mostly chronological, but not quite. Okay, so obviously a key building block from the last century is neural networks. Almost all of the advances you see in machine learning at the largest scale and in the capabilities you see computers have is based on sort of neural network-based computation. And these are sort of made up of artificial neurons. They're loosely based on how real neurons behave in some ways, but they're sort of very imperfect reproductions of how we even understand real neurons to behave, and there's lots we don't understand. But they are sort of one of the underlying building blocks. And another key building block is backpropagation as a way to optimize the weights of the neural network. By essentially backpropagating errors from the output the model gave you to the output you wanted the model to give you, really gives this effective algorithm for updating the weights of a neural network to minimize errors on training data. And then because of the generalization properties of neural networks, you can then generalize to problems or particular examples the neural network has not seen. So those two things really are key to a lot of the deep learning revolution is backpropagation and neural nets. So one of the things that I and some other people worked on in 2012 was really this notion that maybe if we were to train really, really big neural networks, they would be even better than small ones. And so we had this hypothesis, and in 2012, we decided it would be kind of fun to train a very large neural network and see if we could do it using an unsupervised learning algorithm. And so we trained this large neural network, which is about 60x bigger than the previously largest known neural network in 2012, using 16,000 CPU cores. At that time, we didn't have GPUs in our data center. We had a lot of regular old CPU computers. And what we saw was that this unsupervised training objective, followed by some supervised training, actually gave a 70% relative improvement in the less thinly contested ImageNet 22K category. Most of the ImageNet results you hear about are in the 1,000 category section. This was more interesting, perhaps, because it has 22,000 very fine-grained categories. And this was quite a significant advance and kind of, proved our hypothesis of larger models being more capable if you sort of put sufficient training computation behind them. As part of doing that work, we developed our first sort of neural network large-scale infrastructure systems project. This was called Disbelief, D-I-S-T, belief, partly because it was distributed over many machines for a distributed computing system, but also because our colleagues didn't really think it was going to work. So it was a little bit of a play on words. But really, when you're training these large models, and the model doesn't fit on a single computer, there's a few different ways you can imagine parallelizing that computation. The first is you take your model, which typically in a neural net you have many layers of neurons, and you can slice them both vertically and horizontally, say, to produce pieces of the model on each computer, and then have communication managed between the edges that cross between the different splits you've made in your model. The other thing you can do is you can do data parallelism, where now you have many copies of the underlying model on different machines, or perhaps combined with model parallelism, each copy being on many machines. And then you partition the data you're training on across those different model replicas. And in the case of what we were doing in Disbelief, we actually had a centralized system that could accept gradient updates from different replicas of the model and would apply them sort of to the parameters. But we actually did this kind of in the not mathematically correct way, because we were just doing this completely asynchronously. Different model replicas would get new copies of the parameters, would compute on a bit of data, would send a gradient based on those parameters and the training data for that batch back to the parameter server. But by then, the parameters have moved because other model replicas have applied their gradient in the interim. And so this is clearly not mathematically correct according to the gradient descent algorithm, but it works. So that's nice. And that's what really enabled us to scale to very large scale models, even using CPUs. In 2013, we used that framework to actually scale up training of dense representations of words using a word embedding model called Word2Vec. And one of the things that is really useful coming out of this particular piece of work is that by having a representation of a word that is a high-dimensional vector, you get two nice properties if you train it in particular ways. One of the ways you can train it is shown at the bottom here, where you can take the representation, the vector representing the middle word, and then try to predict the nearby words from that representation. There's a different version where you can take all the surrounding words and try to predict the middle word, but they both work kind of roughly equally well. But if you train the embedding vectors for words in this way, what you find is that you can then represent words with these high-dimensional vectors, which have two nice properties. One is that nearby words in this high-dimensional space, after you train on lots of data, tend to be related, because you've sort of nudged all of the words related to cats and pumas and tigers into the same part of the 1,000-dimensional space, say. The other interesting thing is that directions are meaningful in this space. So in order to transform a male version of a word to a female version, you go in roughly the same direction, regardless of whether the words are king and queen, man and woman, bull and cow, various things like that. So like interesting linguistic properties sort of emerge from the training process in the directions of the directions between different points in the space. In 2014, three of my colleagues, Ilya Sutskever, Oriol Vinyals, and Kwok Lê, developed a model called sequence-to-sequence learning with neural networks. And so the idea here is you have some input sequence, and you want to try to predict an output sequence from the input sequence. A very classic case is translation, where you have the English sentence, and then using the representation you've been able to build up by processing the input English sentence one word at a time, you now have a dense representation that you start to do what's called decoding of the French sentence. And in the process of doing lots of language sentence pairs of English and French, you can essentially learn to do a language translation system purely from this kind of sequence-to-sequence based neural network. And if you use that to initialize the state of the neural decoder when starting to translate, that actually works. And you scale up the LSTMs and you show that it can work better and better. So in about 2013, I started to get worried because as we were making bigger and bigger neural networks for things like speech and vision and in some sense language, I started to do some calculations of, well, if, say, speech recognition starts to work better, people might use it. And that might be problematic if we actually want to serve a lot of users in the system. So I did a very rough calculation of like, okay, suppose 100 million of our users start to talk to their phone 3 minutes a day. And at that time, the models were big enough you couldn't run them on device. You had to run them in our data center. And I discovered that rolling out a better speech model, we actually had a better speech model at that time that reduced the error rate by 40%, which is an enormous amount in improvement in speech recognition. So we knew it was going to be better if we could serve it to a lot of people. But the calculation I did said 100 million people, 3 minutes a day, we would need to double the number of computers Google had just to roll out that improvement in the speech recognition model, which is kind of one of our many sort of products. So I started to talk to some of our colleagues in our technical infrastructure group who have hardware expertise, and we decided it would be sensible to build a more customized hardware for neural network inference. And that was the genesis of the tensor processing unit line. And the first version of this was really specialized for inference only. So it used very reduced precision. It had only 8-bit integer operations in its multiplier. But really, the target was, let's build something that's really good at low precision linear algebra, and that will be useful in serving a lot of different kinds of neural network-based models. And you don't need all the other kinds of bells and whistles in, say, modern CPUs that make things much more complicated, like branch predictors or caches of various kinds. You can instead just try to build the fastest and smallest dense linear algebra, low precision thing you can. And sure enough, that was what a largish team produced, was a TPU that was 15 to 30 times faster than contemporary CPUs and GPUs at these kinds of tasks, and 30 to 80x more energy efficient. And by the way, this is now the most cited paper in ISCA's 50-year history, which is pretty impressive because it was only published in 2017. But this has really started our foray into more specialized compute for machine learning models. Then we said, well, it would be really good to actually scale things up and also focus on training and not just inference. And so that's where we started to think about really more like machine learning supercomputer-based systems that have really high-speed interconnect between a lot of chips that are densely connected by this custom high-speed interconnect. So we've now done 5 generations of TPU pods, which are really good for both inference and training. And these connect thousands of chips together. The initial one was 256, then 1,000, then 4,000, and the most recent ones have been around 8,000 or 9,000 chips, all connected together with custom high-speed networks. Since version 4, they've had this like really exotic optical network, so you can take a rack of 64 chips and a rack of 64 chips over there and use funny optical switching and moving of mirrors to make it seem as though they're next to each other in the data center floor, even if they're not. So you can read all about that in that ISCA paper. And we actually just announced last week the latest version of this. This is Ironwood. We stopped naming them with numbers, which confuses me. But so Ironwood has a quite large pod size. It's got 9,216 chips, each of which can do 4,614 teraflops. And so that's 42 and a half exaflops in one of these pods of reduced precision floating points. This is floating point, 8-bit floating point precision, but it is quite a boost up from the previous generation. And so compared to the first training pod, it's about a 3,600 increase in compute capability in the pod in 7 years or something. And importantly, by doing lots of clever circuit design, shrinking of fab processes, lower precision operations than the original TPU v2, we're getting about a 30x energy efficiency improvement per flop compared to the version, the first training pod of 2018. Another trend that's really important is that open source tools for machine learning have really enabled a much broader community to participate in improving those tools, but also to use those tools to tackle machine learning problems of all kinds of different ilk across many different disciplines. And I think TensorFlow, which we released in 2015, PyTorch, I think, came in 2016, and JAX, which is another Google-developed open source framework with a bit more of a functional style in 2017 or 18, I think. These three things, packages, have really, I think, pushed the field forward quite a lot in terms of how accessible machine learning is to people, how standardized sort of the way in which algorithms are expressed in these different frameworks. In 2017, several of my colleagues came up with this very nice observation that in a recurrent model, you have this very sequential process of absorbing one token at a time and then updating the internal state of the model before you advance to the next one. And that inherent sequential step really limits how much parallelism and how efficiently you can learn from large amounts of data. And so they had this really nice observation that instead of sort of taking the current state, advancing it one step and changing that internal state, and then advancing to the next training token and updating that internal state again, they would just save all the internal states. And then they would have a mechanism called attention that would enable you to refer back to all the states you went through in order to get to the particular, if you're 117 tokens in, you have all 117 states that you went through, and you can attend to them and look at which pieces of the representation seem most relevant for the task you're doing, which is often predicting the next token. So this is a hugely influential paper. And part of the reason it's so influential is they were able to demonstrate on machine translation initially that with 10 to 100x less compute and 10 times smaller models, you could get better performance than the state-of-the-art LSTM or other model architectures at the time. And that's a log scale, so that difference is quite large, even though the arrow is small. So that's been really, really important. Nearly all modern large language models that you're hearing about use a transformer as the underlying sort of model architecture with some variations. This is probably not new in 2018, but really came more into vogue in 2018, which was the realization that language modeling at scale can be done with self-supervised data. If you think about any piece of text, and you can use that text to predict other parts of the text. And by doing so, you actually have the right answer in some sense, what the actual text is. And that has been shown, it gives you sort of very, very large amounts of training data. And that's one of the major reasons these language models have gotten so good, is you can get more and more text to train on and improve the quality. And there's a couple of different kinds of training objectives. The first is autoregressive, where you get to look at the prefix of words, and then you try to predict the next word. So many of the models you hear about today are, of this form. And so you can make lots of little training game puzzles for your model. Zurich is blank. Zurich is the blank. Zurich is the largest blank. And the model is forced to use the state that it sees to the left to try to predict the missing word from the context. You can also use kind of fill-in-the-blank style representation, training objectives. So Zurich blank, the largest blank in blank, is an interesting training example. And you can then take the same text and turn it into a completely different training example with different things you have to fill in. Zurich is the blank city, blank Switzerland. And so both of these kinds of training objectives are very useful. The autoregressive one tends to be used more because that's what you're trying to do when you're, say, operating a chatbot and you have a conversation. You don't have the conversation to the right because it hasn't happened yet. You only have the stuff to the left. In 2021, some other colleagues of mine developed a way of mapping image tasks into a transformer-based model. So prior to that, most people were using convolutional neural networks of some form, but essentially they were able to take an image, break it into some patches, and in the same way the word2vec embeds words into a dense representation of those words, they're able to take patches of pixels and do a similar thing where you now represent that with some high dimensional vector for that patch. It might incorporate aspects of the color and the kinds of orientations of things, but those embeddings are learned. And then once you have them, then you feed them into the rest of the transformer model. And instead of using word embeddings for the input here, you use patch embeddings. And that sort of enables you to deal with image data. As you'll see later, when you're training multimodal models, you can actually combine these. So you can put in either text or images, and the visual patches you just embed with a visual model, and then the text patches you embed with a early part of a text model. And you can kind of visualize that the attention operation in the transformer on the right-hand side here is actually attending to kind of interesting parts of the image. When it's asked to say what's in that image, it's attending to the airplane or the dog, or when it's got a snake and there's a lot of kind of confusing stuff, the attention is less focused. It's trying to look at all over the image to see the visual clues that might enable it to predict the right thing. So this has been hugely influential in unifying transformers for text with transformers for images. Another innovation was I and some colleagues in 2017 developed a way to make sparse models, essentially having a very large capacity model, but now instead of activating the entire model on every token or every example, you can activate just a small portion of it. So in our original paper, we actually had quite a lot of experts, like 2,048 experts per layer, and we would activate 2 of those 2,048. And so that's really nice because now your model has this gigantic capacity to remember lots of stuff, and the choice of which things to activate is also learned in an end-to-end manner with backpropagation. And that enables you to sort of have experts that are good at discussing dates and times, another expert that's really good at sort of geographic places, another one that's good at biology kinds of contexts. So that has been really good. And again, similar to the improvement you saw with transformers, we get another algorithmic win with roughly an 8x reduction in training compute costs for the same accuracy. That's line A. Or major improvements in accuracy for the same training cost. That's B. And often when you're reading these kinds of graphs of like some compute budget versus some accuracy score, you want to line up things horizontally because that's the amount less of compute you need to get to the same accuracy. And you can also look vertically, can you actually get much better quality as you're sort of using the same amount of compute. And we've continued to do quite a lot of work on sparse models because we think it's a really important overall direction to have these nice models that have a lot of capacity, but you might only touch 1% or 2% or 5% of the model. In 2018, we started to think about what better software abstractions could we have for these large distributed machine learning computations. And we knew we wanted to train models at larger scale. So each one of these sort of smaller boxes with yellow dots in it, you can think of as a TPU pod. And you want to be able to train a model where you can connect together many of these TPU pods in software and have kind of an underlying distributed system manage the right sort of communication mechanism for when one of these chips needs to talk to another. So when two yellow chips in the same small box need to talk to each other, you use the very high-speed TPU network. When, say, the chip in the upper left box needs to talk to one in the pod in the same building, it will use the data center network within that building. If it needs to talk across buildings, it will use the network that goes between buildings in the same, say, data center facility. And you can even have TPU pods connected together in different regions via, larger, wider area network links, that big orangey red arrow. And by having this nice scalable software that can simplify running these large-scale computations. So in fact, one of the abstractions that Pathways gives to the sort of machine learning developer or researcher is you just have a single Python process. And JAX has a notion of devices. So normally if you're just running on a single machine with, say, 4 TPU chips in it, it just shows up as a process with 4 chips. But what Pathways does when you run it, JAX with Pathways underneath it, all the chips in this entire training job just show up as devices for JAX. So you have a single Python process, and it looks like you just have a single sea of, say, 10,000 or 20,000 TPU devices. And you can run computations on that, and Pathways takes care of mapping that computation onto the actual physical devices. And one of the things we've just done last week was made the Pathways system, which we've used internally for now six or so years, available for cloud customers, for people using our cloud TPU products. Another observation by some colleagues of mine was that thinking longer at inference time is very useful. So in the same way that your third grade math teacher told you to show your work when you were solving problems, because you were more likely to get the sequence of steps right in order to solve the problem correctly, it turns out large language models are the same way. If you just give them an example problem, Sean has 5 toys. For Christmas, he got 2 from his mom and his dad. How many toys do you have now? The answer is 9. That's the one-shot example in the input. And now you're asked a new problem. John takes care of 10 dogs. Each dog takes half an hour a day to walk and takes care of the business. How many hours a week does he spend taking care of dogs? Then the model got this particular problem wrong. It said 50. That's not correct. But if you encourage the model to show its work by, in the one example problem you've given it, actually show it that, hey, this is kind of the sequence of steps to work out the problem. Sean started with 5 toys. If he got 2 toys each from his mom and his dad, then he has 4 more toys. 5 plus 4 is 9. The answer is 9. So that's seems very simple, but it actually turns out that this tremendously helps models become more accurate because they are now encouraged to think through the steps in order to solve the problem in a finer-grained way. And you see that as the model scale increases, the solve rate goes up somewhat if you just use standard prompting, but goes up dramatically when you use chain of thought prompting. This is for a benchmark of roughly 8th grade math level problems. So prompting the model to show its work improves the accuracy on reasoning tasks. And you can think of this as also a way of using more compute at inference time, because now it has to produce all these extra tokens in order to actually get to the right format of answer. In 2014, Jeff Hinton, Oriol Vinyals, and I developed a technique called distillation, distilling the knowledge in a neural network. The idea was you have a really good model, and you want to put its knowledge into a different model, in typically a smaller one. And so the typical way you're training the small model is, let's say you're doing next token prediction. So the prefix you see is perform the concerto for blank. And the true next word is violin. So you can train your model, your language model, with that objective. And if you guess violin correctly, great. If you guess it wrong, then you get some backpropagation error from the training objective. And it turns out that works okay. But if you can use your teacher model to give you not just the correct answer, but a distribution over what it thinks are good answers for this question, for this particular word, it gives you a much richer signal of training. So think of the loss or the objectives you get for the original just violin. You get 0 correct for everything except violin, and then you get a 1. But here, the distribution of probabilities is violin 0.4, piano 0.2, trumpet 0.01, but airplane is extremely unlikely in this circumstance. Concerto for airplane, I don't know, I guess you could have one, but unlikely. And that really rich gradient signal is something that you can use to inject much more knowledge into every training example for the smaller model, and enables you to get to convergence much more quickly. So if you look at some of these comparisons, this is a speech-based setting where you have a training frame accuracy, but what you really care about is the test frame accuracy. Did you predict the sound in this frame of audio correctly? And the baseline with 100% of the training data gets 58.9% on the test frame accuracy. If you strip the training set down to only 3% of the training data, then your training frame accuracy actually goes up because your model overfits to the very small number of training examples you have. But your test frame accuracy plummets because you're in an overfitting regime, and you can't do very well on new test examples you've never seen before. But if you use these soft targets produced by the distillation process and use only 3% of the training data, what you see is you get pretty good training frame accuracy, but you get almost as accurate at the test frame accuracy with only 3% of the data. And this is a really nice property because it means you can suddenly transfer the knowledge of a large neural network into a small neural network and make it almost as accurate as the large one. So this was rejected from NeurIPS 2014. We published it in a workshop and put it in an archive, and it now has 24,000 citations. So we'll take it. In 2022, some colleagues and I looked at different ways of mapping computation onto our TPU pods for doing efficient inference. And there's a whole bunch of variations one can consider. Do you keep the weights stationary in one of the dimensions of the network? Do you keep them stationary in both dimensions so that your weights are now spread across a two-dimensional thing? Or do you gather the weights and bring them to the part? The details aren't that important, but there's a bunch of different ways of doing it. And one of the things that is true is the right choices for how to do this actually depend on a lot of different factors. So one is what is your batch size actually can have a lot of influence on whether one of these three techniques is actually better. And latency constraints can also have a big effect. So if you think about this, we have these three different techniques, weight stationary, X weight gathered, and XY weight gathered, and there's even another one, XYZ weight gathered. What you see is the little dotted things at the bottom of these things are the best thing to do at varying different batch sizes. And that the right answer changes as you change the batch size. And that also means your floating point utilization of your hardware also changes depending on your strategy. And the right answer depends on how large your batch size is. At very small batch size, you want to use a 2D weight gathered in this case. and at larger batch size, a 2D, oh, sorry, I reversed that. 2D weight stationary at small sizes and a 2D weight gathered at larger. So it's just to say that there's a lot of complicated choices in how do you decide how to partition a model and do inference at scale. In 2023, some colleagues of mine developed a technique called speculative decoding. And so the idea here is we're going to use a small drafter model, maybe 10 to 20 times smaller than the larger model, with the idea being that many things are actually quite predictable by a small model. And so we can sequentially predict from the very small drafter model much more rapidly than we can sequentially predict from the very large model. And so we're going to predict the next K tokens with the small model, and then we're going to ask the large model to predict K tokens in a row. And we can advance this generation by as many tokens as match in the prefix of size K. So essentially, if you do this with just the large slow model, it's going to trundle along predicting one word at a time. But if you do this with the there we go. The drafter model, you see the drafter is predicting 4 or 5 words at a time, and then the larger model is trying to predict and will advance as many of the words match that the drafter model created for you. And by doing size K predictions for K words, you essentially amortize the memory overhead of bringing in the weights of the model in order to then predict K words instead of just one. So there's an awful lot of things that have happened, all kind of combining together to really improve the quality of models that people are seeing today. Better accelerator hardware, that's true in TPUs, but also NVIDIA GPUs have gotten a lot better in recent years for machine learning focused applications as well. Software abstractions are really important because they enable you to have kind of these nice layers where you can focus a lot on the performance and the abstractions provided by those things, and then people on top can build useful things without necessarily having to think about the details as much underneath those abstractions. Model architectures, you've seen huge improvements in particular transformers, visual transformers, and MOEs are really heavily used in the most modern models. Training algorithms, unsupervised and self-supervised learning, asynchronous training, distillation. I didn't talk about supervised fine-tuning after you've pre-trained your model, or RL from human feedback or other kinds of computational feedback. That's a super important aspect. Chain of thought, speculative decoding, and inference time compute scaling. All of these are really, really important in the modern sort of era. So now I'm going to talk a little bit about the Gemini models that we've been training and how most of these innovations are used in various iterations of the Gemini models. So Gemini is really a project that started as a collaboration between Google DeepMind, Google Research, and the rest of Google. And we started this in February 2023 with our goal being to train the best multimodal models in the world and use them all across Google. There's all kinds of ways in which these models can help various Google products. They're also available externally through our cloud APIs. And so this is kind of a timeline of what we've been up to since February 2023. We released Gemini 1.0 in December 2023, followed soon thereafter by Gemini 1.5, and so on. So one of the things we wanted was to make these models multimodal from the very beginning, because we felt like just text models were not as useful as models that could sort of understand language, understand visual inputs, understand audio, and also produce all those things. The initial versions of the model did not produce audio as output, but they could take audio and video and images and text as input, and produce images and text as output. We've since added the ability to produce audio output as well. Gemini 1.5 introduced this very long context length so that you can provide inputs that are millions of tokens in length So think about, a 1,000-page document is about 1 million tokens. So you can now put, 50 research papers or a very long book or multiple books into the context window. And one of the nice things about the input data in the model, particularly transformer models, because of the attention mechanism, that information is very, very clear to the model. Unlike training data where you've sort of trained on trillions of tokens and you've optimized your billions or tens of billions of parameters of weights, with those trillions of tokens, you've kind of stirred them all together and you've lost a little bit of the fidelity of the exact pieces of information there. But in the context window, that information is very clear to the model and enables it to sort of extract and summarize and reason over that data much more capably than other kind of data. And in Gemini 2.0, as I said, these models build on a lot of these innovations. So we use TPUs, we do cross-data center training across metropolitan areas using pathways, using JAX on top of that. The distributed representations of words and image data is super important. Transformers, sparse mixture of experts, and distillation. And a lot more things besides. But really, these all kind of come together in our model training recipe and our model serving recipes. Just about a month ago, I guess, we released Gemini 2.5 Pro, which is our most recent model. And this has been, pretty well received because it has, pretty significant leap forward in some of our, various benchmarks that it performs on. It's gotten, a lot better at coding compared to our previous Gemini models. And actually there's a arena for how to compare model quality across different models that is run by LM Arena, which is a Berkeley-affiliated sort of group of grad students. And they sort of enable users to enter a prompt and then pick 2 random models that they're backed by that are behind the scenes. And then they show the output from both models to the user anonymously. So you don't know which model is which, and then you're asked which output do you like better. So it's sort of a head-to-head competition of language models. And through thousands of trials like this, you can actually get a very good sense of the strength of models, at least in terms of how well do the answers reflect what people using this LM Arena like. And we found it pretty useful. It does correlate quite well with the strength of the models. And so this has a pretty significant ELO improvement over our previous models. And it's actually done pretty well on a whole bunch of independent evaluations that people do across the web and on various sort of more academic-y benchmarks on the left there. We are sadly number 4 on New York Times connections. So we'll have to work on that. But in general, this set of leaderboards covers quite a broad set of areas. Some of these are coding related, some are math related, some are sort of multimodal related. And so we really try to focus on making good general purpose models that are good at a lot of different things. Users are generally enjoying this. Some of this is a little over the top phrase, but whatever. People do seem to like it. In particular, the long context abilities are really, really good for coding, particularly now that the reasoning capabilities of the model are also greatly improved. So having 1 million or 2 million tokens of context enables you to put quite large code bases entirely into the context window and then ask the model to do fairly complicated things like, can you please refactor this for me? Or can you introduce a new feature that has this capability, this sort of property? Also enables you to process other kind of data. So like this bottom person has a data set of 1,000 poems, 230,000 tokens, and then asked a bunch of stuff which requires reasoning over all those poems. And they were quite impressed by that because I guess that's hard. Very, very good. Anyway, so one of the things we really focus on, if you look at the y-axis here, this is the ELO score I mentioned from LM Arena. So higher in the ELO score means a more capable, higher quality model as judged by those users. And then on the x-axis is the cost of a whole bunch of different kinds of commercial models. Importantly, the x-axis is a log scale. So don't miss that important point. Okay. Oh, yes. That really rings a bell. So where you want to be is as far up and to the right as you possibly can. And we produce a series of different models with different quality and cost trade-offs. So our flash models over to the right are generally quite cheap. So they're like 15 cents per million tokens. Our most recent 2.5 Pro model is more expensive because it's a much heavier weight model, costs more for us to run it, but it's still quite affordable for the quality you get. And so generally, we like to see that we have a variety of offerings on the Pareto frontier of this quality cost trade-off, and we're going to work to keep pushing up and to the right there as much as we possibly can. Okay, let me talk a little bit about the organization. What happened? It was there. I didn't do it, promise. So Gemini is a pretty large-scale effort. If you look at the Gemini 1.5 paper, we do have quite a few authors. It's very hard to write a short paper if you have to list all your authors. But truly, it's like really a large-scale team effort, and really everyone here really contributed tremendously to this. And one of the things we've had to figure out was how can we best structure this so we can have that many people be effectively contributing to a single model project. And so some of the structuring techniques we use are to have different areas that people kind of loosely affiliate with. So some people are much more focused on, say, the pre-training process, or on data, or on safety or evals. Not to say that these are very hard boundaries, but generally some people have some affiliation with some of these more than others. So there's overall tech leads of the project. So that's myself, Oriol Vignoles, and Noam Shazir. And then we have a really capable program management and product management team. Although Gemini is kind of a model creation thing, it does have a lot of product implications because we want to release that model into lots of different surfaces at Google. And so interacting with all those other teams about what features do they need, where are they seeing the model perform well, and more importantly, where is it not performing well, and getting feedback from those is something that's really important. And then we kind of have three broad categories of these different areas. One is model development, pre-training, where you're training on a large corpus of text and other multimodal data. Post-training, where you've finished pre-training the model on lots of data, and now you're trying to coax the model into behaving in certain ways with relatively small amounts of data, using things like reinforcement learning or supervised fine-tuning so that it has politeness in the responses that it gives, or has a propensity to get mathematical problems more correct than just looking at the pre-trained model. On-device models is another important one. We have Gemini models running on phones, and that has a slightly different character than some of the larger data center-based ones. The core areas are kind of ones that cross-cut most aspects of Gemini, so training data, evaluations, infrastructure, the code base for research and for model expressing the production model training and inference systems. Serving is really important, longer-term research within Gemini. There's also a lot of research that happens outside of Gemini, and we sort of keep an eye on that kind of work, and our colleagues will say, hey, we have something that might be sensible to consider for the next generation of Gemini. And then capabilities are generally about particular sort of narrower aspects of the model. Can we make it safe and behave well? Is it really good for coding? Can we make it good at vision tasks in particular, or audio tasks in particular? Agent behavior is now a very important aspect of what we're doing. Internationalization, because we want this thing to work well in hundreds of languages, not 5. So these are kind of broad areas. We have, of those people, roughly a third of them are in the San Francisco Bay Area. I'm based in Mountain View. About a third are in London, and a third are in a bunch of other places, including Zurich. But New York City, Paris, Boston, Bangalore, Tel Aviv, and Seattle are some of the bigger concentrations of people, not in the first two areas. Time zones are really annoying. I don't know if you all feel this, but the golden hours between the California West Coast and London, Europe, during the workday are relatively limited. It's maybe 2 or 3 hours a day that you really have sensible meeting times for both sides. And past that, then one side is like, I don't know. Our poor Bangalore colleagues are never in golden hours with anyone else. But it's, but it is a worldwide effort. So there's some benefits to having people all around the world, because when the model is training, there's always someone awake and sort of paying attention to a large-scale training run. Often you might fire off a question to a colleague in London and they're not there, but when you wake up in the morning, they've answered and done a bunch of work on your behalf. So there are benefits, but distributed work is challenging. One of the ways we've been able to make this work is we have lots and lots of large and small discussions and information sharing conducted in virtual Google chat spaces. I'm in 200 of these, so I wake up and I'm brushing my teeth and I get like probably 7 alerts while I'm brushing my teeth in the morning, because my London colleagues are busy at work and excited about sharing things in various chat rooms. We have a slightly formalized request for comments, which is really think of it as anywhere from a 1 to a 10-page document about some piece of work or thread of work or results that have been gotten or experiments they're thinking about doing to sort of get some results. People will give feedback in Google Docs style things. We have a slightly formalized way for some of these to say, yes, we think this should make it into the next generation of our model training or the new recipe. We have leaderboards and common baselines to enable good data-driven decision-making about how to improve the model. So many rounds of experimentation, lots of experiments at small scale. You want to advance the smaller scale experiments that seem promising to the next scale to see if the results kind of hold up and are on trend. Every so often, every few weeks, you incorporate successful experiments demonstrated at the largest scale into a new candidate baseline. You run that candidate baseline, see if it's better than the previous baseline, and does it have any sort of unexpected interactions among the few things you piled in there, and then you repeat. So that's kind of, particularly for some of the pre-training recipe development, that's kind of the way we do that. I mentioned scaling of people, but also training of computing hardware. Scaling of computing hardware is quite annoying. So I'll give you just one example, silent data corruption. So despite the best efforts, given the scale of these ML systems and the size of the training jobs, you will get hardware errors that sometimes are not going to be detected by the hardware. And these incorrect computations, because it's a very large coupled system, from one buggy chip can then spread to the entire model. So non-deterministically producing incorrect results, which can happen for particular pieces of hardware, which can happen on any piece of hardware randomly due to various background radiation kinds of aspects. These become worse at scale with synchronous stochastic gradient descent, and it can spread bad results. So one of the things we do is as we're training, we monitor the norm of our gradients. And if we see large spikes in that, we get concerned. So is it justified to be concerned? We don't know. It's certainly a large gradient relative to the ones we've seen recently. And you can also get anomalies with no silent data corruption error. So the first one was actually a silent data corruption error. And the way we detect that is we rewind a few steps and we replay in a deterministic manner. And if we see the same result, then we say, well, it must be in the data. It's probably not hardware failures. If we see a different answer, though, that's concerning because everything's supposed to be deterministic when we replay. And so in this case, we did see an anomaly in the gradient, but we replayed it, and we actually saw that the same large gradient value occurred in the replay as well. Now, you can also detect SDCs if you just happen to replay without an anomaly, right? So this is probably like the low bits of your exponent getting flipped by an error rather than the high bits. The high bits being flipped is bad because then all of a sudden you have 10 to the 12th in the gradient when you expected a 0.7. Yep, okay. I'm going to skip that and give you some examples of what these models can do. So they can help fix bugs in your code, which is nice. This person uploaded their entire code base, all the issues, and like it identified the urgent thing. I guess it was replaying, it was calling some handler twice. And so the code added a flag to say, has the handler been called? And if it hasn't, then call it. In context learning, so Kalamang is a language spoken by about 200 people in the world. And there's a woman who wrote a PhD thesis on a grammar of Kalamang. There's no effectively written internet training data on Kalamang. But what we've observed is that if you put this book into context in the model and then ask it to translate English to Kalamang or Kalamang to English, it can actually do about as well as a human language learner who's been given the grammar book and a dictionary for Kalamang to translate. So that's kind of nice because it shows in-context learning at the level of I put in a 400-page PhD thesis about a topic the model has no idea about, and it actually is able to sort of make sense of Kalamang and translate it with that. Video of a bookshelf to JSON. It's kind of fun. You might not have thought of that as an input method, but you can do that. It's kind of good. Video understanding and summarization. So you can actually put in fairly long videos. 1 million tokens is about 2 hours of video. The prompt is in a table, please write the sport, the team and athletes involved, the year, and a short description of why each of these moments in sports are so iconic. And the model gets to see the pixels of the video and the audio track. And it's like an 11-minute video, I think. And so then the output of the model is that, which is, probably more sort of text extraction, structured data extraction than you thought you might be able to get out of an in-context video. So I think people are not yet clued into the fact that you can actually take multimodal data like that and do pretty interesting things. Digitization of historical data. I just saw this the other day. You can take weather data that looks like that from 100 years ago and just say, please give it to me in JSON. And it will do that. They've done it for 144 tables, and that cost them 10 pence. But now they're able to actually sort of unlock all this weather data. Okay, code generation via high-level language. So here's the prompt we're going to give to our Gemini 2.5 model. P5.js to explore a Mandelbrot set. That's the prompt. Oh, can't. Oh, I'm so sad. Why is it not able to do that? It was working before. Oh, I'm not on the Wi-Fi. It's true, I'm not. Well, anyway, it makes a really nice interactive visual Mandelbrot displayer explorer like that. And then I will skip over the next thing, which, oops, sorry about that. I'm going to skip to a very brief part of this because I'm now running longer than I thought. So now that we have these models, what will this all mean for us in society? And I think it's a really important set of topics. So I and 8 other co-authors recently got together and wrote this paper called Shaping AI's Impact on Billions of Lives. So a bunch of computer scientists and people who with machine learning backgrounds from academia, like big tech companies and startups. And we wanted to propose what the impact of AI in the world could be given directed research and policy efforts. A lot of people in this space are thinking about what will happen with AI if we're just laissez-faire. Will we all be doomed, or will we, have incredible advances? I think really a pragmatic approach is to say, let's, as society and machine learning researchers and practitioners and experts, all work together to try to shape things so that we get the best aspects of AI and minimize the downsides. And really that was what this paper was intended to be, is a discussion of how might we do that collectively. So, and there's the audience. It's all of those people. And we interviewed 24 different experts in 7 different fields: employment, education, healthcare, information, media. Okay. So, for example, we talked to former President Barack Obama, Sal Khan on education, John Jumper, who we talked to him before he won the Nobel Prize, but he won the Nobel Prize later. Neil Stephenson, Dario Amodei, Bob Wachter. And we uncovered 5 guidelines for AI for public good. I will ignore everything after this, but you can see shapingai.com. There's an archive paper from that site that I think is a pretty nice discussion of what will happen in a bunch of different areas, including employment, education, healthcare, or what could happen in some of those areas. And it's pretty important for us to all work together to get this all right. And with that, I will conclude by... We also proposed some nice milestones of what people should work on in some of these areas. That was part of the motivation of the paper. So these models are becoming incredibly powerful and useful tools. And I think you're going to see continued improvement in this as there's more investment and more people in the field doing research, and those sort of advances get incorporated into the leading models. You're going to see even more capable models. This is going to have a dramatic impact in a lot of areas. And it's going to potentially make really deep expertise available to a lot of people across a lot of different areas. And I think that's one of the things that is most exciting, but also kind of disconcerting to some people, is that expertise being widely available. And but done well, I think our AI-assisted future is really bright. All right. Thank you.
Thank you very much for the great talk. A little token of appreciation from the department.
Thank you so much.
Some chocolates and a Systems Group
chocolate.
T-shirt.
I love coming to Switzerland because I get chocolate and a T-shirt. Thank you very much.
Yeah. And we'll now proceed to the Q&A. So we have one mic and we have one cube that we can toss around. And we've discussed that we'll sort of also try to prioritize students, especially for questions. If you can, raise your hands if you have questions, and you can point in a general area, and my aim is probably not that great anyway.
Okay. Nice. Well done.
Hi. Thank you so much, and especially for the last paper you presented.
Oh, yeah. Hold it into your mouth.
Just like this?
Yeah, perfect.
There we go. So Thank you for the talk, and especially the last paper. It's very important, I think. And so on that point a bit. So AI safety is definitely on our minds, I think. And it's super unclear, especially from outside, for example, big research labs, what would even be positive, what would be really impactful. So maybe from the perspective of really making sure everything goes well, everything is in human control and everything, what would you do as maybe a PhD student starting a thesis, a professor with a bunch of research grant money, or even a startup, like let's say you could acquire a startup this year, what would it do in the area of AI safety?
Particularly in the area of AI safety.
Yes, exactly.
Yeah. So, I mean, I think AI safety is a pretty broad topic.
Yeah.
I think there's a bunch of concerns about the increasing capabilities of these models being able to enable people to do things that they wouldn't otherwise be able to do, that are somewhat nefarious or undesirable from a society perspective. So I think some of that can be addressed with some technical means, but I also think that there's going to need to be policy-based and regulatory-based things that impose some restrictions on some aspects of that. In terms of one of the topics that we covered in the paper was about misinformation and public discourse. And there, I think, there's clearly a ability for AI models to create more realistic misinformation in the world and enable people to create it at mass scale with, lower cost. Misinformation is not a new thing. You could always create it, but now you have these tools that enable sort of more realistic and more rapid creation. So that is definitely an issue. I think there's a corresponding research question of how do you detect misinformation that is perhaps generated by a different machine learning model. There's also some questions about turning the problem onto a more positive spin. One of the things we suggested in the paper was there's actually some early evidence that AI models can be used to enable more constructive discourse in online forums. And so that's an area where I think looking at how could AI models sort of encourage more positive conversations, more identify misinformation in the flows of conversations that people are having with each other. These are some of the things that I think are pretty interesting, but there's a whole bunch of ideas in that paper that I think are worthy of study. And I don't think the solution is necessarily going to be purely technical for all these problems. Okay?
Yeah, thank you.
Yep. And send the cube over to him, but we'll take someone else for the moment, if that's okay.
Sure, yes. Where was the question here?
I thought there was one over here. Yes. Yeah, there we go.
Should I?
Yep.
All right. So when I go to social networks, I'm very hype, right? And I see messages that like the ones that you saw. So these LLMs are truly incredible. However, in my day-to-day work, when I try to use AI or LLMs, I'm often disappointed. Who needs training? Is the LLM that needs more training, or is me? I'm asking wrong.
It's an excellent question. I suspect the answer is a bit of both, right? I mean, I do think, using these tools, like first, the arc of progress in these models has gotten quite steep, right? So the Gemini models from 8 months ago are not nearly as good as the Gemini models now. And so sometimes people develop an impression of what the models are capable of from their previous experience trying to ask them to do something complicated, and they failed miserably. But now that might be something that is on the border of possibility or actually will work really well there. So I think part of it is, looking at what the current models can do, not what the ones of ancient history 8 months ago can do. Another aspect is becoming facile with how to coax the models to do what you want, right? It's quite interesting that with like a one-page carefully crafted prompt, you can almost create a completely different application of a general model than if you craft a different one-page prompt. One-page prompt might say, can you take this video contents and please make me an educational game that reflects the concepts explored in the lecture video? And it will actually, in some cases, do create a fully working software-based game that highlights the concepts in arbitrary lecture or scientific video. It doesn't always work, but that is kind of at the frontier of possibilities now. 30% of the time it might work or something. But also more training for the models will help because then the models are going to get better. And I think you're seeing this from Gemini 1 to 1.5 to 2 to 2.5, a lot of progress. And I suspect Gemini 3.0 models and beyond will be substantially better than the current ones. And that's a general trend in the industry is the models are becoming better. You with the cube.
Yep, thanks for your talk. I noticed on your slide where you summarized all of the innovations in AI, you listed hardware, you listed algorithms, you listed all the improvements, but data was absent. And there's lots of concerns in the field that data might be the new bottleneck. I'm curious about your personal opinion on this. Is it a bottleneck? And if not, how do people get by? How do we get past scraping all of the internet?
Yeah, I guess I didn't list data, but it has been really, really important. It's just there's not like a specific artifact generally to point to for a lot of the data-related work. It's really about curation of high-quality data that we spend a lot of time on, say, within the Gemini project. I think there's concerns I've heard of we're running out of high-quality data in order to improve the capabilities of these models. And I find that not very credible at the moment because first, there's an awful lot of data we're not training on right now. So if you think about all the video data in the world, that's, we're training on some video data, but it's a very tiny fraction of, say, the YouTube corpus. And that's only some of the video in the world. So I don't think we're running close to running out of raw data. The other thing I would say is an ML research problem is there's a whole bunch of work I think we can do to get more quality improvements from the model per unit of training or per token of training data, right? If you think about, we were just discussing this in a session earlier, you have a 2-sentence description of how to add numbers together, right? So the model is just trained to absorb that by predicting the next token. But that doesn't generally mean it's actually learned the algorithm for adding 2 numbers together in a deep and sort of algorithmic way. It's got a next token predictor for predicting the rule, but in some sense is oblivious to the actual algorithm. And so I think if you think about what you would really want the model to be able to do, it would be to read that algorithm and then sort of build a representation internally that enables it to run that algorithm when it needs to. So that would be extracting way more value out of those 15 tokens than what it is currently. So I think there's lots of room to go. The other thing I would say in this space is in the improving ImageNet convolutional neural network era, people were training on 1 million images with 1,000 categories. And one of the ways they would make the models more powerful is they would make many, 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 many passes over that training data. The textual data corpus we have is large enough that we're not able to computationally afford to make lots and lots of passes over it. But with improving hardware capabilities, you might be able to make 50 passes over the data instead of 3. And that would probably improve the qualities of the model. But we don't know how much and so on.
Yeah, thanks a lot for the super interesting talk. Where in your personal life or work life do you use AI most, and where do you use it least because it doesn't work yet? Like, what are you surprised by on both ends of the capability spectrum? As you in your work as an employee of a research lab or leader? Sorry.
Yeah, I think where I personally use it and where many of my colleagues use it is helping to write some bits of code. I often tend to ask it to do things that are, not super complicated. I think with the more capable models, I should start venturing out, as this gentleman perhaps should, to more and more expectations of what the model can do. But it will sort of do a reasonable job of writing sort of test cases for code I've written or extensions of things that are straightforward. Seeing it, I've used it to generate images for various kinds of things. I think I used it for this kind of thing. I use it to summarize papers, or I put in a large piece of textual content and ask it questions about that. But I think, more and more you're seeing people integrate use of these models into things they find that they're able to do that are useful for them. And I think that's sort of the general trend in society.
And where doesn't it work? Where have you tried it and it's doesn't work, doesn't...
I have asked it to do more complicated coding questions, and sometimes it works, sometimes it doesn't. And then you're like, oh, okay, I understand why it didn't work, because that's pretty complicated, and it would have taken me a long time to figure out. So,
thanks.
Okay. How about right there? Yeah.
Thank you.
Hang on. Let's get a microphone.
Thank you for your presentation. It was super interesting. And I was wondering, for the upcoming research, what would be the most interesting part to focus on? Is it improving transformers for the computer vision area more important, or AI safety regarding to prevent hallucination of large language models would be the most important part that you are going to focus on?
Yeah, I think one of the beauties of this field is it's not that there's just one important problem. There's many, many sort of important problems. And so one of the sort of meta things I do when I'm trying to think about research topics is to try to pick something that, if I make progress on it, or we as a collective set of colleagues make progress on, something important will be advanced, right? So I think avoiding sort of incremental things where even if the best possible outcome happens, you're kind of like, You want to avoid that. But I think all the areas you mentioned and like 50 other ones besides are really important. Other ones that I'm personally thinking about, like how can we have much more efficient inference hardware? How can you have much larger context windows for these models than 1 million tokens? How do you identify higher quality data? How do you scale infrastructure? How do you do asynchronous training in a better way, in a distributed fashion with low bandwidth between the systems? How do you have interesting, more exotic, sparser model structures than just kind of branch out to experts and come back together, which seems kind of like relatively too simple for truly sparse, interesting model structures. So I think there's like 50 other ideas I could rattle off. You should pick something you're really excited about and that you think will matter.
Thank you.
Yeah, one more question. I don't know. You pick. How about we get one farther in the back, because we have ignored the back. The gentleman in the black T-shirt there. And it's close enough to throw. There we go. See? Oh, we're 2 for 2 on our passing. I love it.
Thank you very much for the presentation. It was incredible. My question is about what's the next challenge? Because I see that these models are getting better and better in all the benchmarks gradually. But is there some sort of binary challenge, some outcome that they are not yet able to do? I don't know, formal reasoning, some activity that's, let's call it the next breakthrough.
Yeah, I mean, I think one thing that's not quite a discrete step, but I think is going to be very hard, is the current models. If you think about what we're going to want the models to be able to do, it's to operate sort of a bit autonomously and to do fairly complicated things that you ask the model to do with relative independence, right? Can you go off and plan me a visit to Zurich for 2 days because I have a couple extra days and I want to do some fun stuff? And then, that is a little ambiguous. It might require the model to use some tools to go figure out, well, what is the Zurich place and what can I do here? And then I think what you're seeing is the models are capable of breaking down complex things into a few steps, maybe doing some limited amount of tool use to chain some things together in order to sort of do those relatively simple tasks. But you're not seeing models able to take a very complicated thing and break it down into 50 substeps on its own, use many, many complicated tools in order to accomplish some major piece of thing that might take you, 2 months, right? And I think there's a huge, vast difference between where we are now, which is it can do those kind of 3 or 4 or 5 step tasks with maybe 60 to 70% accuracy, and it can do a month of work in 1,000 steps with 95% accuracy, right? I mean, I think that is where people would like to be able to get systems going, but it's a very vast gulf between where we are now and what one imagines would be possible, but is definitely not now. So I think that's maybe a sort of continuum rather than a single thing that suddenly now you can do this. But you will see more and more capabilities of the models as they can do 10 steps things with 90% accuracy as an intermediate point. All right.
All right. Thank you very much. Let's thank Jeff one more time for the great talk.